In this video, we're going to talk about the series circuit analog 5.1.4. So let's start with the um, equation so far, putting the two equations together for the LR and the RC circuit that we've had so far, that we can turn that into L di dt plus Ri plus 1 over CQ is equal to E of T, where E of T is our electromotive force. And then we want to get everything in terms of Q, remembering the I is equal to dQ dt, which makes di dt d2q dt2. And so then we can transform this equation into a second order linear differential equation with constant coefficients. Which looks very much like what we were just doing in 5.1.3 with driven motion, where L stands in the place of M and R stands in the place of B and 1 over C stands in the place of K, and E of T stands in the place of F of T. So we have, this is just an extension, an analog of what we were just doing in 5.1.3, but we're going to apply it to series circuits. And if I haven't said that so far with LR and RC circuits in the past, these are series circuits. These are not circuits that are in parallel, they're series circuits. So I want to make sure that I make that statement here. All right, let's look at number 49 from the textbook. And it tells us that we want to find the charge on the capacitor in an LRC series circuit at time t is equal to 1/100th of a second. So find Q of 1/100th of a second as our ultimate goal when L is equal to 5/100ths of a Henry and R is equal to 2 ohms, and C, our capacitance, is equal to 1/100th of a farad, and E of T is equal to 0 volts. So this is going to be something that's going to be homogeneous. Q of 0 is going to be equal to 5 coulombs for our initial charge, and I of 0, our initial current, is equal to 0 amps. And so we have an equation that looks like this. Just go ahead and write it in terms of Q's. And that becomes, when I do my division by my L and write everything with constant coefficients, this becomes Q double prime plus 40 Q prime plus 2000 Q is equal to 0. And I'm gonna go ahead and find my auxiliary equation. Squared plus 40m plus 2000 is equal to 0. So m squared plus 40m equals negative 2000. Half of this squared is going to be 20 squared is going to be 400. Going to add to both sides here to complete the square, which gives me m plus 20 squared is equal to negative 1600, giving me m plus 20 is equal to plus or minus 40i. This isn't complementary because it's an auxiliary, or it's a homogeneous equation. So this is my Q of t is equal to All right, let me finish this up. M is equal to negative 20 plus or minus 40i. So Q of t is equal to e to the negative 20t times C1 cosine of 40t plus C2 sine of 40t, like that. And then we're going to find Q prime, which is the same thing as I. So I of t be negative 20 e to the negative 20t times C1 cosine of 40t plus 40, sorry, plus C2 sine of 40t. Now we leave the outside alone and differentiate the inside. It's negative 40 C1 sine of 40t plus 40 C2 cosine of 40t. And that means the I of t is equal to e to the negative 20t times negative 20 C1 plus 40 C2 cosine of 40t plus negative 40 C1 minus 20 C2 sine of 40t, right? And negative 20 plus 40 cosine, negative 40 minus 20 sine. Excellent. So Q of 0 is equal to C1 is equal to, we were told that that was 5. I of 0 is equal to negative 20 C1 plus 40 C2. And we were told that that was equal to 0. So 40 C2 is equal to 20. Sorry, this is negative 100 plus is equal to 0. So 40 C2 is equal to 100. And C2 is equal to 5/2. All that here, we can come back and write Q of t is equal to e to the negative 20t times C1 is 5 cosine of 40t plus 5/2 sine of 40t. And we were asked to find out what Q of 100th of a second is. Using my calculator, I found that to be approximately 4.568 coulombs. And then we also want to find the first time in which the charge on the capacitor is equal to 0. So we can graph this if we want to find it that way. I went ahead and converted this into the other form that only has sine in it by making Q of t equal to e to the negative 20t times the square root of 5 squared plus 5/2 squared times sine of 40t plus arctangent of 2. And so Q of t is equal to 5 root 5 over 2 e to the negative 20t sine of 40t plus, and this is about 1.107. We're going to set that equal to 0, and I'm going to find that the only part of this that could be equal to 0 is when sine of 40t plus 1.107 is equal to 0. So that happens when 40t plus 1.107 is equal to a multiple of pi, n pi. So 40t is equal to n pi minus 1.107, and t is equal to n pi minus 1.107 over 40. Clearly, when t is 0, this is a negative time value that I don't want. So the first time that I'm interested in is when n is equal to 1. And again, using my calculator, that's about 0.0509 seconds. It's S for seconds. Moving along to the next problem, which is number 51 for me. I'm going to do for you, and that is right here. We're going to find the maximum charge on the capacitor, given that L is equal to 5/3 of a Henry. Our resistance is equal to 10 ohms. C, our capacitance is 1/30th of a farad, and our E of t is equal to 30 volts. Initial charge is equal to 0 coulombs, and initial current is equal to 0 amps. So I'm going to write our equation here that this is 5/3 of Q double prime plus 10 Q prime plus reciprocal of 1/30th is 30, and that equals to 3. Sorry, this is not 30, this is 300. And so that's going to become Q double prime plus 6Q prime plus 18Q is equal to 180. This is non-homogeneous this time. M squared plus 6m plus 18. We're going to find that auxiliary equation first. Don't have any factors of 18 that add up to be 6. So I'm going to complete the square. Half of the middle number squared is 9. It's m plus 3 quantity squared is equal to -9. So m plus 3 equals plus or minus 3i. M is equal to -3 plus or minus 3i. Now I'm going to need a complementary and a particular solution here. So my QC is going to be equal to e to the -3t times the quantity C1 cosine of 3t plus C2 sine of 3t. And that means that my IC, which is my Q prime C here, is going to be equal to negative 3t times C1 cosine of 3t plus C2 sine of 3t plus e to the negative 3t times a negative 3 C1 sine of 3t plus 3 C2 cosine of 3t. So I of C is going to be equal to e to the negative 3t times, then this is going to be negative 3C1 plus 3C2 cosine of 3t plus and a negative 3C1 minus 3C2 sine of 3t, like so. And now we need to pick a appropriate QP. The right-hand side is just a constant. So QP is just going to be A with QP prime equal to 0. QP double prime is equal to 0, giving us 0 plus 0 plus 18A is equal to 180. So A is going to be equal to 10. So that means QP is equal to 10. And that means that IP is going to be equal to 0. So because it's that QP prime there. So QT is going to be QC plus QP. So it's going to be 10 plus e to the negative 3t times C1 cosine of 3t plus C2 sine of 3t, and my I of t is just going to be this thing that I called IC because there's nothing to add to it. So I of t is going to be e to the negative 3t times negative 3C1 plus 3C2 cosine of 3t plus a negative 3C1 minus 3C2 sine of 3t. Great, let's figure out what Q0 is here. So that's 10 plus C1 that needs to be equal to, say, 0. So C1 is equal to negative 10. And I of 0 is going to be equal to negative 3C1 plus 3C2. That's also going to be equal to 0. So this is going to be 30 plus 3C2 is equal to 0. 3C2 is equal to negative 30. C2 is also negative 10. So this is going to be QT is equal to 10 plus e to the negative 3t, and then this is negative 10 cosine of 3t minus 10 sine of 3t. Because it has a GCF, the book is going to want to write that as 10 minus 10 e to the negative 3t, and just leave the part in here that is cosine of 3t plus sine of 3t. And now when we take the derivative of this I of t, we're going to want to go back and make our substitutions for our C1 and C2 in I here. So I of t is equal to, and then stick in -10 there and -10 there, 30 minus 30, that's 0. So this is 30 plus 30, that's 60. That's 60 e to the -3t sine of 3t for our I of t. And then when we want to find the maximum charge on the capacitor, we have a couple of options. We could graph Q of t and find the maximum, or we can use our first derivative test or second derivative test, something like that. I'm going to use the first derivative test and say, where is I of t equal to 0, since it's the first derivative of Q, and I want to find maximum charge. Remember that this is a graph that is looking like this, where its wave is reducing in amplitude as it goes on. So the first maximum that I come to is going to be the maximum charge for QT. So I will look for where I am increasing and then decreasing first time on QT, or on Q prime of t, which is I here. So let's go ahead and let's look first for where I is 0. So that's going to happen when sine of 3t is equal to 0, and 3t is going to be equal to n pi. So t is going to be equal to n pi over 3. Starting with n is 0. The smallest time can be a 0. Then I'm going to have pi over 3, and then it's going to be 2 pi over 3. And so between 0 and pi over 3, if I look at the value, this is always going to be positive. It's not going to change the sign of this. So sine between 0 and pi is a positive value, so I'm increasing here. And then pi to 2 pi, that's negative, increasing, then decreasing. So there's a local maximum here, and that's going to be what I'm looking for. So I'm looking for Q of pi over 3, and I stick that into my calculator to approximate it with the equation that I found for Q of t, and I get that that is about 10.432 coulombs. Now I'm going to go all the way over to number 57. My next example here, so 57 tells me to find the charge on the capacitor in the LRC series circuit when L is equal to half of a Henry, R is equal to 10 ohms, my capacitance is equal to 1/100th of a farad, my E of t is 150 volts, initial charge is equal to 1 coulomb, initial current is equal to 0 amps, and then so we want to find the equation for Q of t, and then we want to find what the charge on the capacitor is after a long time. So as t goes to infinity, what's our steady state for our charge as opposed to our transient state, which is the part that's making it go up and down and up and down. So what is it that it's approaching there? So we have our equation here will be 1/2 q double prime plus 10 q prime plus the reciprocal of 100th is 100. Q is equal to 150. And so that turns our equation into q double prime plus 20q prime plus 200 is equal to 200q is equal to 300. Our auxiliary equation is going to be m squared plus 20m plus 200 is equal to 0. M squared plus 20m is equal to negative 200. Half of the squared is 100. That's 100. M plus 10 squared is equal to negative 100. So m plus 10 is equal to plus or minus 10i. M is equal to negative 10 plus or minus 10i. Writing my complementary solution for my charge, QC is going to be equal to e to the negative 10t times C1 cosine of 10t plus C2 sine of 10t. And then we want to go ahead and find the derivative of this while we're here. So IC is equal to negative 10 e to the negative 10t C1 cosine of 10t plus C2 sine of 10t, and then we leave this part alone and differentiate this part. And then we go ahead and combine our like terms, and we end up with e to the negative 10t times negative 10 C1 plus 10 C2 cosine of 10t plus, and then we have negative 10 C1 minus 10 C2 sine of 10t. And that lets us find our complementary part of our solution. We know that our particular part here is just going to be a constant. So QP prime will be 0, QP double prime will be 0. If we come back and we look at our equation, that means that we have 200A is equal to 300, and A is equal to 3/2. So that means that QT is equal to 3/2 plus e to the negative 10t C1 cosine of 10t plus C2 sine of 10t. And then we can go ahead and find Q0 over here. So Q0 is going to be 3/2 plus C1, and that needs to be equal to 1. So C1 equals negative 1/2. I of t is going to be just whatever I called IC there a second ago, because there's no Q prime of P. So it's going to be e to the negative 10t and negative 10C1 plus 10C2 cosine of 10t plus negative 10c1 minus 10c2 sine of 10t, and I of 0 is going to be negative 10c1 plus 10c2, and that needs to be equal to 0. So let's just write it this way: negative 10c1 equals negative 10c2. C1 equals C2, so C2 also equals negative 1/2. That means that my Q of T is going to be equal to 3/2 plus e to the negative 10t times negative 1/2 of cosine of 10t minus 1/2 sine of 10t. Again, because there's a GCF there, the book is going to write this as 3/2 minus 1/2 e to the negative 10t of cosine of 10t plus sine of 10t, like that. It's a really sloppy looking 10, sorry. And we didn't need any of that part that's transient to answer the question about what happens as the limit of Q of T as T goes to infinity to find my steady state, because as soon as we found this constant part out here, that was the answer, because all of this transient part is going to 0. So that's going to go to 3/2 of a Coulomb for my charge. But they wanted us to find the equation for the charge on the capacitor at any time before we answered the question about what happens as time gets, after a long time, the charge on the capacitor approaches 3/2 of a Coulomb. All right, so that's it for this video, and we'll come back next time and start talking about some things in 5.2, which are some applications of some boundary value problems. So I look forward to seeing you for that next time. Probably just a few examples. I haven't done much with boundary value problems. Definitely haven't done any linear models with boundary value problems. I'll come back and I'll just do a few examples of those for you before we move on and go into the next section, the next big unit, which will be starting with 6.1. We'll come back and talk about 5.2 for a little bit first. All right, see you for the next video.